All right. Um, in this class, we will continue solving problems related to infinite bodies, and if time permits, we'll also go into semi-infinite bodies. So, as per your syllabus, only chart solutions are included. So, in the last class, I have showed you some equations for solving problems to find the temperature distribution in an infinite solid, which was called as the um, infinite series summation solution for Fourier number less than 0.2, and for Fourier number greater than 0.2 you can use the first term approximation. So that I have introduced only so that you know what are all the things that are available. uh, Using those equations actually will take some time, because as you have seen, there is a transcendental equation involved where you have to find the root of an equation and then substitute in other things. So it involves certain steps, mathematical knowledge to solve those equations. Therefore, it is not included in your syllabus. So all you have to do is use the chart solutions, provided the Fourier number is greater than 0.2. That condition exists because the chart solution or the first term approximation equation is applicable only for Fourier greater than 0.2. Okay, so in the last class, one student asked, there was a doubt about the infinite plate. The heat transferred in the infinite plate, the formula given in the data book is rho Cl multiplied by delta T. And what I was saying and what I used to solve in the class was rho C uh, 2L, 2L, where 2L is basically the entire thickness of the plate. So uh, if you use the data book equation, then you'll get heat transferred only half of what I got. So the correct thing is to use the entire thickness, not half of the thickness as given in the data book. So in the data book, instead of L, you correct it as a 2L. Okay, because in the figure given in the data book, 2L is the thickness of the plate. Okay, that correction I wanted to make and complete that particular problem. Now we'll move on to the next problem in the slides. All right. So here we have the second problem. So basically, I'm solving three problems. One on uh, flat plate or a slab. Another one is a cylinder, and third one will be a sphere. So here the problem reads like this: estimate the time required to cook a hot dog in boiling water. Assume that the hot dog is initially at 6 degrees Celsius, that the convection heat transfer coefficient is 100 watts per square meter Kelvin, and that the final temperature is 80 degrees Celsius at the center. Treat the hot dog as a long cylinder of 20 millimeter diameter having the properties as given. Okay, so basically we are asked to find the temperature, the time required to cook a hot dog. Here it's the hot dog. The similar question can be asked about cooking eggs. Okay, so hot dog is boiling water is cooked in boiling water. Here we also cook egg in boiling water. So similar approach, except that egg is not exactly a sphere, but for the sake of the analytical treatment, we approximate egg as a sphere. So that is what we do. But anyway, in this case, hot dog, what's the shape of a hot dog? It's given that it's a long cylinder. Hot dog is a long cylinder of 20 millimeter diameter. You see, the length of the cylinder is not given, but the diameter only is given. And we are told that this is a long cylinder. Okay. So we have to solve this problem. Now you see the key thing is assume that the hot dog is initially at 6 degrees and the 6 degrees Celsius. That means the hot dog was removed out of the freezer and then it is dropped in boiling water. And inside the boiling water, the convection coefficient is 100 watt per meter square Kelvin. And the final temperature at the center. You see, this final temperature at the center is 80 degrees Celsius. That means center should reach 80 degrees Celsius. If center is reaching 80 degrees Celsius, what will be the surface temperature of the hot dog? Will it be greater than 80 or less than 80 or equal to 80? That's a question. For a hot dog which is dropped in boiling water, what's the boiling water temperature? We know it's 100 degrees
100.
Celsius. Okay, so when we drop this hot dog at 6 degrees Celsius in boiling water at 100 degrees Celsius, eventually it will, if you leave it for a long period of time, the entire hot dog will reach 100 degrees Celsius. But we are talking about one time instance where the center temperature is 80 degrees Celsius. My question is, if it is 80 degrees Celsius at the center, what will be the surface temperature? Will it be greater than 80, less than 80, or equal to
Greater.
80? Greater than 80. That's the most sensible thing. If the hot dog is a lumped system, it will be equal to 80. Okay, so that's the difference between lumped system and the distributed system. And see, this 80 degrees Celsius is not just a random number. It has certain importance. All food, whenever we before consuming, all food has to be heated to at least 70 to 80 degrees. That's the agreed temperature. So each and every part of the food must be either either 80 degrees Celsius or greater than 80 degrees Celsius. The reason is that all the bacteria, it gets killed at this temperature. The bacteria cannot survive temperature above 80 degrees Celsius, though it is important to heat any food item to 80 degrees Celsius. Okay, so that's the reason of this 80 degrees. Okay, so now the question is, for this hot dog to center temperature to reach 80 degrees Celsius, what is the time needed? That's the question. Okay, so let us start solving the problem. We have a pail of boiling water, and inside the boiling water there is a long hot dog, and the temperature, sorry, what's the diameter of this hot dog? 20 millimeter diameter. Okay, the heat transfer, boiling water, so T infinity is 100 degrees Celsius. H is also given as a 100 watt per meter. Initial temperature is given, Ti is 6 degrees Celsius. Final temperature or the desired temperature at the center line is 80 degrees Celsius. So we are now interested in the center line temperature initially. Okay, so we have some properties given. So we know that we are asked the time. So basically this is a transient problem. So the first step in any transient problem is to find out the Biot number. So Biot is Hx by K. H is the heat transfer coefficient 100. X is for a cylinder. What is X? X is the outer radius divided by 2 divided by K. So we know the diameter is 20 millimeters. So radius is 10 millimeters. So H is 100. Radius is 10 millimeters. Convert that to meters. Divided by the conductivity, we have it as 0.52. So we are checking the Biot number to decide whether it's a lump system or not. So this is 0.96, which is greater than 0.1. Therefore, the hot dog is not lumped. It's not lumped. It's a distributed system. Okay. So we'll have to. We are told that it's a long cylinder. So the word long cylinder, and we all are also given the diameter. So this means that it is an infinite cylinder. So we'll have to use the concepts of infinite cylinder. So now let us, you open your data books and turn to page number page number 77. Page number 77 of the data book. Okay. So in page number 77, you have a graph where you are given, where the title of the graph is long cylinder, temperature, time history at center line. So this is the center line. So at this center line, whatever this graph gives are the values on this center line. Okay. So temperature, time history at the center line. So temperature on the y-axis, Fourier number on the x-axis. Remember, Fourier number is a non-dimensional way of representing the temperature time. Okay. So using the parameter h r naught by k, this particular graph of temperature difference ratio and the Fourier number is plotted. So from this graph, we should be able to identify, or we should be able to find out what is the time required for the center temperature to reach 80 degrees Celsius. So we have on this graph, we have T naught minus T infinity. See, T naught is the center temperature minus T infinity divided by Ti minus T infinity. Ti is the initial temperature. And here we have the Fourier number. Fourier number is alpha tau by R naught square. R naught is R outer. Okay, that's the capital R is used in the data book, so that's what I'm using. And the parameter is h r naught by k. Okay. Now, see, I want you to notice the difference between this h r naught by k and this. Both of them look like a Biot number, but this one is h r naught by k and this one is h r naught by 2k. So this value will actually be double of this value. But since the graph is given in terms of h r naught by k, we'll also separately have to calculate this one. Okay, so let us do the calculations here. H r naught by k. H is 100. R naught is 10 millimeters, 10 power minus 3 meters, and the k is 0.52. Okay, so this is 0.92. And Fourier number, as of now, we don't know the time. Okay, so we'll have to find the time. Therefore, x-axis value we don't know yet. Okay, so we know the y-axis value. What is T naught minus T infinity? T naught minus T infinity divided by Ti T infinity. This is T naught is the center temperature. We want the center temperature, this one, to reach 80 degrees Celsius. So 80 minus T infinity is 100. That is the boiling water temperature divided by initial temperature is 6 minus 100. So how much is this? 0.213. Okay, so what we need to do is we know this HR naught by K is 1.92. So let us say this curve is having a value of 1.92. And on the y-axis, we know this value as 0.213. Okay, so what we have to do is from here, project a line onto this parameter, and from there, read the Fourier number value. And from the Fourier number, we don't know the time. We know the alpha value. Alpha, we are given the properties, no? Density, specific heat, and the conductivity. We can calculate the value of alpha. And tau is not known, R naught is known. So we read the value of Fourier number from the graph, and the value of tau can be calculated from the Fourier number. So we'll do that now. Okay, so what is the Fourier number? So you all find out and tell me what is the Fourier number from your graphs. Use the data book, page number 77.
Sure, about 0.75.
How much?
0.75.
About 0.75. Okay. Let me also see once. See, the HR naught by K is 1.92. We have a curve of 2. So you can take something, you have curve of 2 and curve of 1.5. Okay, so somewhere in between you can take it approximately. That will be HR naught by K. And 0.213 is there. That's the ratio of the temperature differences on the y-axis. So you can also do that approximately. And then you will have somewhere, yeah. So between actually it's between 0.7 and 0.8 and somewhere somewhat close to 0.8. See, this thing will differ from person to person. Okay, so let me say this is 0.78. So that's the Fourier number we got. So we from start, Fourier number is 0.78. Now Fourier number is alpha tau by R naught square is equal to 0.78. Alpha is K divided by rho Cp. So value of K 880 K by rho Cp. K is 0.52. Density is 880. 335. Is 1.764 multiplied by 10 power minus 7. What are the units of alpha? Thermal diffusivity. Units of alpha. It is meter square per second. So thermal diffusivity gives us an idea of how quickly the heat can penetrate. So much square meters it can cover in a second. That's the meaning of thermal diffusivity. So I'll use that here. 1.764 multiplied by 10 power minus 7 multiplied by tau divided by R naught. We have diameter 3 millimeters R. So equal to 0.7. So what is tau? Tau is 442.2 seconds. So usually we convert this to minutes. This is 7.37 minutes. Okay. So approximately 7.5 minutes. So that is how long it takes for the center to reach 7.37. That means you will have to wait at least for 7.37 seconds to fully cook this hot dog. So that's the meaning of this answer. So the first part of the question is answered. Is there any other part? That's it.
So I have a doubt.
Yeah.
Sir, in this, when we found out the Biot number, so why did we divide radius by 2? Sir, it's already radius is already half of diameter.
No, by definition, it is the Biot number is for a cylinder. For a cylinder, the radius, the characteristic length. X is the characteristic length for the for a cylinder, and that it turns out to be R by 2. See, X is, I will write it. Characteristic length by definition is a volume divided by area. Okay. For a cylinder, volume is a pi R square L, right?
Yes, sir.
Divided by area is, what's the area? 2 pi R L. Okay, so have this R by 2. Okay.
All right, sir.
For a sphere, it is R by 3. So I have given this in one of the Biot table on the right bottom. For a plane wall having thickness 2L, the characteristic length is L. For a cylinder, it is R by 2. For a sphere, it is R by 3. Okay.
Yes, sir.
So this is how we got this. For a sphere also, if you calculate that ratio, volume by area, volume is 4/3 pi R cube and area is 4 pi R square, you will get R by 3.
Okay, sir. Got it.
All right, so this is the solution for this problem. We're moving on. We have here a spherical hailstone. Hailstone is basically, you must have observed under certain climatic conditions, this ice blocks fall and they are round in shape. So a spherical hailstone that is 5 millimeters in diameter is formed in a high altitude cloud at minus 30 degrees Celsius. If the stone begins to fall through warmer air at 5 degrees Celsius, how long will it take before the outer surface begins to melt? What is the temperature of the stone's center at this point in time, and how much energy has been transferred to the stone? A convection heat transfer coefficient of 250 watt per meter square Kelvin may be assumed, and the properties of the hailstone may be taken to be those of ice. Okay. So this problem again has got an importance from the weather viewpoint. So what happens when the hailstone falls through the atmosphere? The atmosphere actually offers some resistance for this fall. And also you see the atmosphere is warmer than the hailstone. Therefore, there will be heat transfer from the atmosphere to the hailstone. Also, because of the friction, some heating takes place. So that is because of the viscous heating that is called. So two reasons for the hailstone to become hot. One is because of the higher temperature of the atmosphere, or because of the temperature difference between the atmosphere and the hailstone itself. Second one is the frictional heating. So this frictional heating will be higher and higher if the velocity is higher. Now this has got another application also. You must have heard of this re-entry vehicles, re-entry spacecrafts, right? You must have heard, or you must have watched that in several movies. The space shuttles carrying humans, when they go to the outer space and carry out the necessary studies, and when they want to return back, all the astronauts will be seated in this particular re-entry cabin that is supposed to enter the atmosphere and take them to a safe space where they can land. Now, what happens is the spacecraft is initially in a vacuum. The space is vacuum, so there is no atmosphere. There is no resistance for the flow. Now, once the spacecraft enters the surface, so when enters the atmosphere, so where is the atmosphere? Approximately, it's about 100 kilometers, or the atmosphere starts or atmosphere ends at about 100 kilometers over the Earth's surface. So once the spacecraft enters this atmosphere and it is entering at a very high speed, so because of that, what happens is because of the friction, the surface of the re-entry vehicle becomes very, very hot, and it becomes red hot. And to protect the people seated inside the cabin, there are certain heat shields, insulations, and so on. If this heat shield fails, then the inside of the cabin also becomes hot, extremely hot, so that the people inside cannot tolerate that heat and they eventually will die. So that's what happened in the case of Kalpana Chawla. Okay, so this particular problem that we are trying to solve has got, as I gave you this example, another application of re-entry vehicles. But just remember, there are two reasons for the heat transfer to take place in this particular problem. One is the low temperature of this hailstone and the slightly higher temperature of the atmosphere. Here it is 5 degrees Celsius. Another reason for heating up will be the viscous drag or friction we can call. So that also causes the heating. So because of these two reasons, there could be melting taking place of the hailstone. We are asked to find out how long will it take for the surface of the hailstone to melt. Now we all know that here the hailstone's temperature is minus 30 degrees Celsius, but the melting point is 0 degrees Celsius for ice. So the question basically is initial temperature is minus 30 degrees Celsius. The ambient temperature is 5 degrees Celsius. When will the surface reach 0 degrees Celsius? So when will this minus 30 degrees Celsius become 0 degrees Celsius at the surface? That's basically the question. And in this problem, I said there are two reasons for heating, but in this problem, the only reason for heating we are considering is the heat transfer, not the friction. Okay. So we'll try to solve this problem. Hailstone, as mentioned in this problem, is spherical in shape. So we'll assume the same shape. Here, there is this hailstone, spherical in shape, and it's 5 millimeter diameter. And it is the initial temperature is minus 30 degrees Celsius and the ambient temperature is 5 degrees Celsius. The heat transfer coefficient is given as 250. Okay, yeah, that's pretty much what we have. Now we are not given the properties of ice, so you will have to read the properties of ice from the data tables. So can you tell what are the properties of ice? Allocate the properties of ice from the data book. Tell me which page to look at.
So 16.
Okay.
There are actually two values of ice given here.
Yeah, one at 0 and one at minus 20 degrees. Our temperature is minus 30 degrees, isn't it?
Yes, sir.
See, it doesn't really make much difference in the ultimate thing. So, but when you have this kind of 0 two values, you will have to take the one which is closer to the actual temperature given to us. So initial temperature is minus 30 degrees Celsius. What we have here is minus 20 degrees Celsius. So we'll take the properties at minus 20 degrees Celsius here. So for ice, K is 2.03. Density is given dash here, so we'll take the at 0 degrees Celsius, 920 kg per meter cube, and the specific heat is 1945 joule per kg Kelvin. So these are the properties.
Can we not use interpolation between 0, 20 and 0, minus 20 and minus 30?
If we do the interpolation, what is the we will get? We'll get at minus 10 degrees Celsius, right?
No, so in that case, the cross multiplication normal.
You want to do extrapolation, you mean?
Yeah.
Yeah, not necessary. Not necessary. It won't make much difference. That 10 degrees Celsius doesn't really make much difference. Okay. So don't worry about that. We'll take the minus 20 degrees value properties. And it's not real. Interpolation is okay. Extrapolation somewhat results in erroneous results. So better avoid unless it is absolutely necessary. All right. So now let us calculate the Biot number first. So as always, the step is to calculate the Biot number. So ultimately, what we want is the surface temperature is Ts. Ts is supposed to be 0 degrees Celsius. For that, what is the time? That's the question asked, isn't it? How? So we'll have to work towards that. So since this is a transient problem, the first step, as always, is to estimate the Biot number is hx by k. And since this is a sphere, the formula will be hr by 3. So h is 250 and r is 2.5 millimeters. So convert that to meters divided by 3 divided by the conductivity is 2.03. All right. So this is 0.103. You see here, it's actually actually quite close to 0.1, isn't it? So we may actually be tempted to use the lumped system. In fact, for this, we can actually use the lumped system, but we'll go by this infinite sphere method, and let us see how it works out. So let us go by this charts now once again for a sphere. The charts for the sphere are at are in page number 80, 81, and 82. So in this problem, we have to find several things. One is how long will it take before the surface begins to melt? That means how long will it take for the surface to reach 0 degrees Celsius? Then what is the temperature of the stone center at this point of time? So we have to find out the center temperature when the surface starts melting, and how much energy has been transferred to the stone. So 3 questions to be answered. Okay, so let us try and answer these 3 questions. We have the first chart is time history at the center. The second chart is time history at any radius. Okay, so what we'll do is at surface we will we'll find what is the time, what's the at any radius. So we'll try to find the time at the surface. So on the surface, we have Biot number as, sorry, no, not Biot number. The ratio R by R naught is equal to 1. Okay, so we'll take that. And what is the x-axis here? Is Biot HR naught by K. Okay. And the y-axis is T minus T infinity divided by T naught minus T infinity. Now what is T naught? T naught is, can anybody tell what is T naught? What's the meaning of T naught? Not the value. What's the meaning of T naught? T naught is the surface temperature, center temperature. So in this particular problem, before we identify the time necessary for the surface temperature, we can find the center temperature first. So what's the parameter here we have here? The parameter here is R by R outer. Okay. So for the surface, R by RO, what is the value here? At the surface, on this surface,
1.
is equal to 1. So this is equal to 1 here. Okay. And the Biot number H R naught by K. H R naught by K is H is 250 in R outer is 2.5 multiplied by 10 power minus 3. K is 2.03. This will be 0.307. Okay. So 0.307, let us say it is somewhere here. 0.307. And this is 1. So project a vertical line onto this R by R naught is equal to 1, and on the y-axis, read this value. So all of you open your chart in the data book. It's in page number 81. So this is in page 81. Of the data book. So from this, you tell me what is the ratio of T minus T infinity divided by T naught minus T infinity.
0.87 something.
0.86.
Okay, yeah, this happens to be 0.86. Okay. T minus T infinity. Now this T is at R by R outer. T naught minus T infinity is 0.86. So surface temperature, we want it to be 0 degrees Celsius at the surface. Minus T infinity is divided by T naught is something we don't know. T naught minus 5 is equal to 0.86. From this, calculate the value of T naught. Tell me how much T naught is. Minus 0.81 degrees Celsius. Okay, even though the surface, see that, even though surface is at 0 degrees Celsius, the center is slightly cooler. It's at minus 0.81 degrees Celsius. Okay, so this is the center temperature, 0.8 minus 0.81 degrees Celsius. So we have kind of answered it, but not directly. See, we're asked what is how long will it take before the outer surface begins to melt? So we didn't find out what is the time taken. We actually found out when the surface melts, what is the center temperature. Now what we have to do is at this center temperature, how long will it take? So that means we'll have to use the chart that is available on page 80 to find out the Fourier number. Remember, whenever the time is asked, Fourier number is the one you need to use. So the Fourier number is available in the time history at the center chart, which is in page 80. So now we'll have to use the chart on page 80. So we'll use the chart on page 80. So that chart looks like this. On the x-axis, we have the Fourier number, and on the y-axis, we have T naught minus T infinity divided by Ti minus T, and the parameter is H R naught by K. R naught by K, we already know it is 0.307. And T naught minus T infinity divided by Ti minus T infinity. So T naught is how much now for us? It is minus 0.81. Okay. So minus 0.81 minus 5 divided by initial temperature is minus 30 minus 5. So how much this is? 0.166. So this value is 0.166. So identify this point 0.166 here. And from this draw a horizontal line onto this 0.307 line, and from there drop a perpendicular onto the Fourier number and find the value of the Fourier number. Fourier number is, as I told, it's a indirect, is a non-dimensional way of representing time. So from the value of the Fourier number, we can calculate the time. So tell me the value. This is in page number 80. It is somewhere between 2 and 3, Fourier number 2 and 3, but somewhere closer to 2. So we'll say Fourier number is 0.4. Fourier number value is, our formula is alpha tau by R naught square. Now we'll have to calculate alpha. Calculate alpha. Alpha is K by rho Cp. K is 2.0 is 920. Cp is 1945. .13 or minus 6 per square per second. So 1.13 multiplied by 10 power minus 6 multiplied by tau divided by R outer is 2.5 limit, 2.5 millimeters. Is Fourier number, which is 2.4. This implies that time. Can calculate the time. What's the time here? Time is 13.27 seconds. So the moment the hailstone starts falling into this atmosphere of 5 degrees Celsius, it takes 13.27 minutes for the surface to start melting. At that 13.27 seconds, the other question is what will be the center temperature, which we already found out the center temperature to be minus 0.81 degrees Celsius. Okay. So at this time, the center temperature is minus 0.81. That is, center temperature is sub-zero, whereas the surface temperature is 0 degrees Celsius. Okay, so that's how we are need to solve it. And finally, we are asked another question: how much energy has been transferred to the stone? So what is the heat transferred? So for that, you need to use the Grover chart. So I think slide here. So heat transferred. To use Grover chart. Page 82. So what do we have here? On the y-axis, we have q by q naught, and on the x-axis, we have h square alpha tau divided by a k square, which is nothing but a Biot square divided by Fourier, where Biot is HR by K. Okay. So we know Biot and Fourier number, so we can locate the point, and the parameter is HR by K. So something like this, HR naught by K. This also we know. So from here we draw a line here, and from here see this. Read the value of the ratio Q by Q naught. We'll have to estimate Q naught. Q naught is equal to maximum possible heat transfer. Is a mCp delta T. So mass of the hailstone, which is density multiplied by the volume. Density multiplied by the volume multiplied by Cp multiplied by delta T. So density is we have taken it as 920 multiplied by volume is 4/3 by r cube multiplied by Cp. What was the Cp value? We took 1945. Multiplied by delta T is how much? 5 minus of minus 30. So this is the temperature difference, 35 degrees Celsius. So this will be the value of Q naught. You have to calculate that. R is 2.5 millimeters. Okay. Now Biot square Fourier is how much? Biot means HR naught by K. H R naught by K multiplied by the Fourier. So we did this calculation earlier. HR naught by K is
0.226.
7. I think Biot, this entire thing must be squared. So this is squared multiplied by a Fourier number. So this is how much? 0.226?
0.226.
Right. 0.22. Okay. So this value should be 0.226. This is 0.307. Accordingly, read this value and find the value of Q by Q naught. So Q by Q naught, you read the value here. So this value, bring it here, and then estimate the value of Q. Q naught is already known. We could calculate Q naught here. Okay, so you complete that part of the problem. Okay. I hope you are following. You can see that each problem takes a considerable amount of time, even though we are using the chart solution. Remember, we are not using the one-term approximation. Another thing you see, the Fourier number we got is 2.4 in this problem. And it satisfies the condition that Fourier number is supposed to be greater than 0.2. So .78. It again greater than 0.2. That means the chart solution is appropriately used. Remember, chart solution is only for Fourier number greater than 0.2, and we are within our limits or within our rights to use the chart solution.
Sir, the parameter which we have is Biot number, which is given as 0.2 and 0.5. We don't have 0.307 or 0.3.
We don't. No, you will have to interpolate. That's all. There's no other way.
Okay, sir. No, but plotting the graph, I mean, there's no graph over there.
For 0.2 and for 0.3, yeah? What was the
0.307? We don't have any curve for that.
Yeah, we have one for 0.2 and one for 0.5, no?
Yes, sir.
Take it somewhere in between. Somewhere in between. See, this thing is bound to be approximate only. Each of you will get a different answer. If you are around that ballpark value, that should be sufficient. See, unless you use the one-term approximation, the mathematical equation, you will all have different answers. Okay. So next class on Monday, I will take up semi-infinite solids. Okay, so I will take your attendance now. Your attendance. Mrutunidhi,
Present, sir.
Lash,
Present, sir.
and Cherian,
Sir.
Sudan,
Present, sir.
Dilip,
Present, sir.
Siddharth, Srivatsan,
Yes, sir.
Mitrayan,
Present, sir.
Lanivel, Shant,
Present, sir.
Kalagan,
Present, sir.
Present, sir.
Above Current,
Present, sir.
Present, sir.
Sri Krishna, Pain,
Praveen present, sir.
Adil Sinju,
Adil present, sir.
Vedi,
Chhatrapati present, sir.
Hassan, Ayush Tripathi,
Present, sir.
Harshavardhan, Anant Kumar,
Present, sir.
Pa,
Present, sir.
Molly Singh,
Present, sir.
Vania,
Present, sir.
Rohit, Raman, Al,
Sriraman
Present, sir.
Dipesh,
Present, sir.
Nirudh Venkat,
Yes, sir.
Kumaran,
Present, sir.
Sundar Krishna,
Present, sir.
Arnav, Kunti,
Present, sir.
Niket,
Present, sir.
Badri Narayanan, Vito, Ajit,
Present, sir.
Raghav,
Present, sir.
Rahul.
Present, sir.
Firoz,
Present, sir.
Present, sir.
Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Tishwar,
Yes, sir.
Jay Prakash,
Yes, sir.
Pooja,
Present, sir.
M. Kumar,
Yes, sir.
Karan Sarvesh,
Present, sir.
Karan Ajay,
Present, sir.
Paul Simon,
Yes, sir.
MC Krishna,
Present, sir.
Tesh,
Present, sir.
Shreya,
Present, sir.
Karan Dev,
Present, sir.
Arun, Kunal Rao,
Kunal present, sir.
Kunal Rao,
Sir, Kunal present, sir.
Dinesh Krishna,
Yes, sir.
Vedant Madhur,
Present, sir.
Anand,
Present, sir.
Pani, Iya Vasan,
Present, sir.
Shivani, Kalai Priyan,
Present.
Shankar Narayanan,
Present, sir. Manish present, sir.
Santosh present, sir.
Kumar,
Present, sir.
Ash Kumar,
Present, sir.
Dik Prasanna,
Present, sir.
I Kaustab,
Present, sir.
Nahalyan,
Present.
Sarvesh Krishnan, Ilsi Femina,
Present, sir.
Effort Journal,
Present, sir.
Manoj.
Present, sir.
I'll call absentees once again. Siddharth,
Present, sir.
Palanivel,
Present, sir.
Pratik Krishna,
Present, sir. Present, sir.
Sir, Chintan present, sir.
Hamza Hassan, Harshvardhan, Sai Rohit, Badri Narayanan,
Sir, Badrinaran present, sir.
Vito,
Present, sir.
Shivani,
Sir, she mentioned in chat box.
Sarvesh Krishnan,
So he replied in chat box too. So.
all right. So I'll check the chat box. All of you can leave the class now. We'll meet again on Monday. I'll solve a couple of problems in semi-infinite solids and then move on to two-dimensional heat conduction. Okay. So next week also we'll be doing some calculations, a new type of calculations probably. So you don't want to miss those classes.
Thank you, sir.
Thank you, sir.
Thank you, sir.